In this video, we'll learn about Fischer projections. Fischer projections can also be used as a way to represent a molecule with chiral centers. Instead of drawing the tetrahedral configuration, we draw the molecule as like a T-shape, where everything is 90 degrees. And the horizontal lines represent bonds coming out of the paper. The vertical lines represent bonds going into the paper. So drawing our Fischer projection in our T-shape, where we draw just the straight lines, it's implied that the two on the horizontal plane are coming out towards you, they're wedges, and the two that are vertical are dashes. And Fischer projections are a useful tool, particularly when we're looking at carbohydrates. So as I said, sometimes they facilitate a comparison of stereoisomers faster than if we draw a tetrahedral. So the way we can think about our Fischer projection, if I draw my tetrahedral, and we'll say we have priorities 1, 2, 3, and 4. We're going to be looking at it kind of from the bottom side here. So if you have your model kit, try and look at it from this angle. When you look at it from this angle, our carbon in the center has atoms 2 and 3 are going away from you, and atoms 1 and 4 are coming towards you. Which means if we draw without the wedge and dash, we draw our T. Which would look like that. If we draw two different Fischer projections, we can easily see if they're different chiral centers or not right away. It's much easier than with the tetrahedral where we might have to rotate. So with our Fischer projections, we do some rotations, but the rotations are not quite the same as with the tetrahedral. If we rotate 180 degrees, you get the exact same compound. For example, let's say we're given this Fischer projection. If I do a 180-degree rotation, so I'll take the molecule and rotate it 180 degrees like that. We end up with this configuration. So now if we were to draw it back at that tetrahedral, we end up with these two structures. Where our priorities go 1, 2, 3, 4. 1, 2, 3, 4. So as we can see, both of these are going to be R. Remember this one, since that hydrogen is pointing forward, it looks S, but it's really R. So you can see if we take that Fischer projection and I rotate everything 180 degrees, I get the exact same compound. But if I rotate it only 90 degrees, I get the enantiomer. So again, let's draw a couple of Fischer projections. Same compound. So that's only 90 degrees, which means HCOOH. OH, methyl. So again, if we try and draw those in their tetrahedrals, we can see that now they're going to be slightly different. So now if we try and take these two and make them look like each other, I'm going to take the hydrogen and rotate it down so it's in the same plane as this hydrogen. So that way they're in the same spot. And so if we do that, do a quick rotation about everything. What happens is we've held the carboxylic acid the same. The hydrogen is now down. Our OH is up. And our methyl group is going back. So you can see that the carboxylic acid and the alcohol group are in opposite spots now. They're opposite of this, which means now you've changed the chiral center. You've changed it from being an R configuration. You've changed it from being an R configuration into an S configuration because you changed where two of the groups are. And so with our sugar molecules, as I said, sugar molecules or carbohydrates are usually drawn in a Fischer projection. It just makes it easier to draw them and to visualize the different diastereomers of a sugar. And the way sugar molecules are typically drawn is they're drawn with the higher oxidized carbon at the top. So your aldehyde or ketone is usually towards the top. And then you draw your chain coming down. And then across that chain, that's where the OHs and the hydrogens are drawn. And then the last one, we draw CH2OH. So this is typically how we draw a sugar molecules using a Fischer projection. So you should start to learn how to do Fischer projections. That way when you get to carbohydrates, it's a little bit easier. So now how do we draw mirror images with Fischer projections? When you draw mirror images with a Fischer projection, it's really easy. All you have to do is change the two groups on the horizontal. So let's say we had our good old compound here, which by the way is lactic acid. So if you work out a lot, you might have heard about lactic acid building up in your muscles. Now you know what it looks like. If you switch those two groups on the horizontal, now you have mirror images. So here we have R. Here we have R, lactic acid. And here we have S, lactic acid. And so you can see this if we look at the tetrahedral. If you want to double check, you can see the RNS configurations here. So by just switching those two groups on the horizontal, we've now created enantiomers. Now I'm sure you're asking yourself, do I really have to switch it to tetrahedral every time I'm looking to figure out R and S? No, you do not. You can figure out RNS configuration by looking at the Fischer projection itself. So let's look at an example. Let's say we had our compound here. And we assign the priorities. 1, 2, 3, 4. And so if you're connecting together, it kind of goes in that direction. So it looks like it's S. But if we were to take it out of a Fischer projection and draw it back as the tetrahedral, we can always double check. So far you've seen me do the switching really quick. Let's kind of go through it step by step. If we take it from the straight lines to the wedges and dashes, remember the horizontal are wedges. And the vertical are the dashes. So if we remember a tetrahedral, I have my locations like that, and we're looking at it from this direction. So if we're looking at it from this direction, these two bonds here, those are my H and my OH. Because remember, we're looking at it kind of up from the bottom here. So that makes my OH here, my hydrogen here. And then the aldehyde and the alcohol, those would be my back two here, because they're away from where that I is. And so now if we're trying to assign our priorities, let's see if it's still S. 1, 2, 3, 4. So now you can see it's going in the opposite direction. Actually, R. So spoiler alert, it wasn't S. Which means when we're looking at our Fischer projections, you can still assign R and S, just whatever you assign, remember it's the opposite. So if it looks S here, it's really R. Because if you drew it out as a tetrahedral, you'd see it becomes R. So remember, apply the R&S rules backwards when you're in a Fischer projection. When you're in a tetrahedral, apply them like normal. When you're in a Fischer, it's really the opposite. Now let's look at enantiomers of our Fischer projections. So two images that are enantiomers are mirror images if you rotate them 180 degrees and they look different. So let's try a structure here. Let's say we had this compound. And I draw its mirror image. So what I'm going to do is take one of those mirror images. We'll take this one and rotate it 180 degrees. When we rotate it 180 degrees, that means my CH3 is now on top. CH2, OH is on the bottom. OH is on that side, hydrogen on that side. So you can see this one does not look like that one. The two groups on the vertical are opposite of each other, which means they're enantiomers. Which means we have a chiral compound. And this is a quick way to see if you have chiral compounds or achiral compounds. So let's try one more. 5CH3, CH3, bromine, bromine. And my hydrogens. Draw its mirror image, because technically we have two stereocenters there. And then we do our rotation. Now, they look identical. Since the rotated compound and the original one are identical, we consider this achiral, because it does have a mirror plane that runs through it. That mirror plane, you can see, is right there. And so we can use Fischer projections to draw longer chains. When we're drawing a longer chain, there's one rule you want to think about. You want to rotate every other carbon. Don't rotate every carbon, every other carbon. So if we look at glucose, and I recommend get a model kit out. Look at it from a model kit. We have our glucose here. So we're going to rotate every other carbon, which means when we're looking at it, we're going to start looking at it from this perspective. So we always start with that aldehyde at the top, the most oxidized carbon at the top. And we have 1. So we have 1, 2, 3, 4 crosses we have to make on it. And then we have CH2OH. So 1, 2, 3, 4, CH2OH. So when we're looking at it, this OH is going away from the I. These two are away. So if you refer back to that first image I drew of a fissure, this would be considered atom number 2, which was our top one, right? The chain here, we want this chain to be the backbone. That's the one going straight down. So that chain there, that has to be number 3, which means this has to be 1 and 4. So if we remember back to that initial Fischer projection I drew for you guys, we can see spot number 4, spot number 4, spot number 1 gets the hydrogen. And then we go to the next one. And remember, the chain has to be the one going vertically. And we rotate every other carbon. So we flip the groups on every other carbon. So what was the dash here now becomes a dash over here, and then over here, and then over here. So you kind of zigzag as you go down your fissure. So our OH is a dash on the second one. Our OH is a dash on the third one. And then the OH is a wedge on the fourth one. So you can see you kind of rotate back and forth. Which one's wedge, which one's dash. And it goes bouncing back and forth as you're drawing your fissure. And you just keep going back and forth like that. So now you're able to draw a long chain in a Fischer projection without too much trouble. So now you guys have learned how to draw from a tetrahedral to a fissure, and then from a fissure back to a tetrahedral. You also have learned how to assign the R and S configuration of a Fischer projection and how to draw longer chains in a Fischer projection.